Right. Hey, okay, let's start the lesson, right. So this is the damped harmonic oscillator. So what we essentially had, we had a hot, in fact no, that doesn't even matter, that's a PID controller, we can just ignore that. This is just it wasn't even a real experiment, it was just a thought experiment, this whole thing, right? But it's based on like a harmonic oscillator, right, which is a spring, right, a spring that's powered. So these are like the physics formulae for that, right? So you've got some function, and if you differentiate, what's the original equation? Oh, this is the analytic solution to a harmonic oscillator, right? But we don't need that shit, because you can just sine wave it in the velocity, right? But this is how something actually looks, right? If you've got something that's there's no drag or anything, and something's moving back and forth, you'd expect it to just do that. So if it's going up and down, when it's here, it's got, in fact no, spring's fine. So here, it's being pulled back to the middle, right? So here, it's got loads of potential energy and no kinetic energy, and here it's got full kinetic energy, and then potential kinetic, right? So it does this graph, right? It goes up and down between the two, but the total energy in the system stays the same, right? So then, we're going to talk about different ways of iterating, right? And it says the first method, right, so you can try and solve these problems analytically, but it doesn't make sense when you're doing, well, it's easier to solve them numerically with a computer, because computers can't analyze shit. But also, when we're doing game development, we'd never do an analytical solution because there's no point, because we want things on a frame-to-frame basis, right? So we're not just, like, we're computing, we're not analyzing when we're doing video games. So the first method is now I use a few methods here. One is the Euler method, one's the Euler-Kromer method, and one's the Verlet method. The Verlet method's really, really good, but Unity and most video games use the Euler method. So this is really relevant, right? So what it does is you have your time at t is 0, and you find your velocity by adding the delta time, so the fixed delta time in Unity, times the acceleration to the velocity. So yeah, you can't have a tiny t, so you have a small step value. So in Unity that's like 0.02 by default. Right, so after your small time h, so after fixed delta time, you now have the displacement t plus h, and you do that by doing h times the velocity and add that to x, right? So you have v times fixed delta t, and that changes that, right? So whatever, that's how it does all the calculations in Unity. But when that happens, this happens, right? So you've got your spring, but the energy in the spring goes up and up because of floating point error. So I'll demonstrate that just briefly in Excel. Let me scroll up. My scroll wheel's fucked. If I type equals 0.5 minus 0.4 minus 0.1, right? Now you might expect that 0.5 minus 0.4 minus 0.1 is actually the number 0, but as we'll find out now, it's 2.77556 e to the minus 17, right? Because machines can't do maths. So when a machine doesn't know what the fuck 0 is, like it can't do calculations properly. So because of these tiny errors, it actually inflates the energy massively because it's so often curving that it blows up and the errors get exponentially bigger. So a way to fix that, look, after 50 seconds the energy's increased 100 times. So then there's this other method, the improved Euler method, and that does this. So it's slightly better, but it kind of is weird. I would never recommend using that, but it's just a different way of iterating. You could implement this in Unity if you wanted, but rigid bodies don't use that, they use the Euler method, right? And then you've got the Verlet method as well, which is this red one here. Wait. This is definitely the wrong way around. Oh, sorry, it's just the color. You can't see the color on the stream. But but this really big one's the Euler, then the red one's the improved Euler, and then the one that's staying about the same as the Verlet method. But the Verlet method, it's a big calculation. Look at this, just for one step, it resolves the simultaneous equation. So it just this giant piece of bullshit. Fuck that shit. All right. So yeah. What's this? Comparison of numerical methods. Oh, right. If you see this, the Euler chroma as well, it stays the same as well. Right, and this is the face plot. Who cares about that graph? That doesn't fucking matter. Right. So anyway, now what we can do is we're now using the Euler method again, where these circles create energy. This is the energy being created here, right? But this thing, we have damping, right? So instead of doing and becoming huge, they instead get fucked, right? So this one is this red one's supercritical damping, in that it's so damped that it takes a while to get there, right? So if you tell it, hey, I want you to go here, then it's gonna be like, and it's like really shit. Like, you never want to be supercritically. Well, sometimes you do. One good thing for supercritical damping is, say I have a menu item, and I want it to like go, then you could supercritically damp it. But that, you wouldn't normally do that. You just slurp, right? Because you don't need this relies on velocities, and you wouldn't need a velocity for that. But sometimes I do use that. Like sometimes I think slurping's easy, right? But if you want something to overshoot, right, then if you see this supercritical damping thing, if you only have critical damping, not supercritical, then it'll overshoot a little. So I use that all the fucking time in my games. Like, if I have something that I want it to just go a little bit over, then I'll add a hypothetical velocity into there, and instead of just moving it by position, I'll keep another variable that is its velocity, and then store that. It won't even be a rigid body. I'll just mark my own velocity and make it overshoot. So the thing is, you just gotta come up with a damping factor. So if you multiply it by like 0.99 every frame, then that's like barely any damping. But like the way I've figured out is, it's pretty much, if you multiply it by about 0.98 every frame, then it won't go to infinite energy, right? It'll carry on roughly the same, right? If you multiply by about 0.2, then you get this overshooting damping. If you multiply by like 0.5 every frame, it'll go like, that'll be supercritical, right? So that's how I do my drag. But if you see this, this thing, yeah, this is like, I've got a force and then I tell it to go to this force. So it's pretty much exactly what you do in a game, right? You'd be like, oh, I want you to move at 0. Oh, no, I want you to move at 20. And you can get there by telling it to adjust its velocity there. Like, using this magic formula, like velocity plus equals the desired velocity minus the current velocity times, say, 0.9f. That will make it get there. It'd take it 90% of the way every frame. If you put 0.1, then it'd get 10% of the way every frame. Right, and then what you do is you do velocity times equals 0.9, right, and then it's damped so it won't overshoot. So now if you want your velocity to go to D, then you can go every frame you set it to D minus V plus equals D minus V times 0.1. Right, and if you want it to if you're interested in getting something to go to a position, what you can do is you can do V plus equals the desired position, right, minus the current position, divided by the fixed delta time times 0.1, and that's the same thing. Because if you integrated 3, you'll get that. And then again, v times equals... So whenever I do an operation like this, I always do like a v times equals 0.9 or something. Because 0.9 is a surefire way. It'll make it move a bit slower, but then you can e.g. put that up to a 0.15. So it's about balancing these two variables, because this one will keep it in check and make sure it doesn't explode. And this one will keep it at a sensible speed when multiplied together with this one. Right. So yeah, this is... If you see this, if you leave it undamped, then it's going to overshoot. So if you actually want something to just oscillate, then you can actually leave no drag at all, and it will... You can just tell it to go to that value, and it will just oscillate around it. So I mean, you always typically want at least a little bit of drag so that it'll move somewhere and like wiggle a little like this. You see what I mean? But yeah, here we're setting it to loads of arbitrary values and making it instantly get there. Alright, and then this stuff isn't really relevant. So there you go, right, there's character, like, force-based controls 101. So, e.g. what I've done here, I'm on the train. Wait. See, you can see I'm on a train, I'm moving relative to the train. Right. If I jump, then I jump at the same speed as the train. Right, and if I jump off train 1 onto train 2, then I'm now moving at train 2 speed, and I can dash off on the track, and now, like, dash between them. Right, and I can do quick dashes like this. So if I put myself over, if I move myself over here, we'll talk about like why forces are really good. And I talked about why forces are really good in my talk on 2D platformer, but I mean it wraps over to 3D. Right, if you see, I can move really slow, or like I can move super fucking slow, right? I can move as slow as I want, or I can move really fast. It's like really fluid, and you get that with force based, whereas if you get velocity based, then you can't do stuff like that. And it's not slippy because there's enough drag. Like here, like tap 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 tap. But if I run, and if I like hold down like this, the left stick and the right stick like that, I'll do perfect circles as long as I keep them in place. And if I change like, if I change the right stick, then it'll change the radius of the circle. Or if I like do this, so that allows like good strafe movement. Okay, and then yeah, and then the jumping as well. If you see, if I do a tiny little hop, right, then I do a little hop, right. But if I hold down a while, then I do a big jump. Or if I hold down mid, then I go mid. You know, like tiny, mid, middest, like high, medium, low. So I get like precise movements. And also, if I go sideways, I get like a little boost in that direction of the jump. And if I dash, right, then I can do like a dash jump, and then I'll go really far, like, whoop. And I can go dash, 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 dash. And because I've got the drag, then I can just, like, when I dash, I literally just set the velocity really high, and then the drag will push me down to a sensible speed again. And I can be sent absolutely flying, and it's fine. It's like that with the, if you see, like, when I'm on the train, let me put myself back on the train. Yeah, I can stop on a dime. Look at that. You see that? I was moving it. Look, I'm moving at full train velocity, right? And I'm gonna walk backwards off this train. Boom, stopped. And that's just the drag that stopped me. Look at that. Like, whoop, whoop, whoop. Dash, 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 whoop, whoop. And I can go whoop, whoop, in and out, and in and out, whoop, whoop. And do some like pro platforming skills. You can dash towards here, whoop. Nah, I shouldn't have done that. But yeah, not only can you truly dash, you can truly dash on a moving train, go on to another moving train, stop. And that's just the character controller itself, like stopping, like it's not like I have to do anything, it's just the drag will always get me. War collisions, like, well,